Hi, everyone. Thank you so much for being here. I'm Nihit. I'm a co-founder and CTO of Refuel AI. My background is in applied machine learning. Prior to starting Refuel, I spent a few years at Facebook helping build and scale their human-in-the-loop machine learning systems for platform integrity. And prior to that, I worked on recommendations and search at Instagram and Facebook and LinkedIn as well. So in today's talk, we'll discuss kind of best practices, common challenges with building human-in-the-loop machine learning systems for platform integrity. As broadly, the problem of detecting and taking enforcement action on various classes of what we'd call bad, illegal, undesirable content or behavior on online platforms. The talk is a distillation of kind of having worked on some of these problems myself, but also just talking to a lot of folks who worked on similar systems, similar problems in other companies. So the agenda for the talk is as follows. We'll start with an overview of the problem and kind of common canonical architectures for building such systems. And then we'll deep dive into 3 key learnings on data collection, model evaluation, and kind of designing these systems for being adaptive and responding to real-world changes fast and effectively. And we'll have some time at the end for questions. So first, the problem overview. The best consumer internet products in the world are successful in large part because of their ability to scale and grow quickly. And with scale comes responsibility to ensure that these platforms, these products, are used in a way that not just kind of obeys and follows laws, but also they're used in a way that is consistent with their values, their principles, and their mission. For example, if you're Amazon, you want to ensure that your platform is not being used for selling illicit drugs, counterfeited goods, and so on. If you're Gmail, you want to make sure that your users don't have to deal with a lot of email spam. And if you're one of those big social media companies, Twitter, Facebook, Snapchat, et cetera, you want to ensure that your users don't have to see a lot of hate speech, misinformation, nudity, scams, et cetera. And this is broadly the goal of platform integrity. The goal of integrity is to reduce the prevalence and the distribution of what we would categorize as harmful content or behavior on the platform. And sort of often this goal is seen as being somewhat in opposition to growth, right? For example, filtering spam or bot accounts might reduce the number of active users on the platform, or preventing advertisers from running certain kinds of ads might reduce revenue and so on. But in the long term, right, these 2 goals, growth and integrity, could not be more aligned. And it all comes down to user trust, right? By reducing harmful content, we are increasing the trust of interactions on the platform. And in the long term, this is critical for growth and for retention. So all integrity systems must solve these 3 key problems in order to be successful. The first is defining what is acceptable on the platform and what isn't. A clear, objective definition of what is allowed and what is not allowed. The second problem is that of detection. Detecting policy-violating behavior and content, typically through a combination of machine learning models, rules, human review. And the third is deciding, taking enforcement action on content that is actually violating policies. This could be everything from just downranking and limiting its distribution, taking down the content entirely, or even disabling user accounts. A somewhat lossy analogy here is that so the policy definition is the written law, detection is the police, and decisioning is the system of courts. Let's talk about canonical architectures for building these systems. So most integrity systems kind of have the following end-to-end workflow. There are triggers for content to enter review. For example, is the entire content stream of new uploads entering review? Is it only user-reported content? Is it only content that's going viral? So on. And then this content typically goes through a combination of machine learning models, rules, human review. And what comes out at the other end is so think of these as ensemble classifiers that encode platform policies. And then what comes out of the other end is one of three decisions. Either we can auto-enforce in case it's a blatant violation, or we can auto-approve in case we're very sure that this is not violating any platform policies, or we'll enqueue it for human review. And then you have human review teams that kind of look at these pending items and then ultimately decide whether to approve or enforce. So most integrity systems tend to be this hybrid of machine learning and some form of human review. And the exact mix sort of varies a lot depending on kind of tolerance for false positives, the maturity of your ML models, and so on. But why this hybrid, though? And it comes down to the fact that machine learning and human review really have complementary strengths. Machine learning wins hands down on metrics like latency, scale, and cost. However, one of the biggest limitations of machine learning models is that they are hard to generalize. It's hard to incorporate kind of real-world context, knowledge of events as they happen, and generalize to kind of completely unknown scenarios, right? And this is where human review strength really lies. Reviewers can be trained to understand the spirit of the policy and make judgments under ambiguity. So how should we construct these hybrid systems? What is a good division of responsibility between machine learning and human review? Let's look at this histogram of model score buckets. There's a few things going on here, but let's step through them. So we have a model that predicts the likelihood of a content violating some policy. And we've bucketized this model scores, as you can see on the x-axis. And on the y-axis, what we're plotting is the volume of content that falls in a given model score bucket. And then within each bucket, we're tracking the percentage of content that is a true positive or is actually violating that policy. And if it trained our model well, kind of we'd expect this percentage to increase monotonically from left to right. So within this, kind of we see broadly three categories of content emerging. Content on the left that is not a violation, and we can auto-approve those. Content on the very right, these are blatant violations, and we can auto-enforce on those. And then there's content in the middle that needs to be reviewed by a human operations specialist. And over time, we want to shrink sort of this mass that's in the middle. So we want to reduce the volume of human review, increase automation, and keep end-to-end performance at parity or better. What does performance mean here, though? Sort of how do we measure success, and what should we optimize for? Enforcement quality ultimately is a trade-off between these three objectives. Recall, we want to catch as much violating or bad content as possible. False positives, we want to reduce those. This is countermetric to the first one. We want to ensure that content that is not violating any policies is not accidentally enforced on. And the third being operational metrics, things like operational expenditure, latency of enforcement, and so on. And we want to make sure that this is within bounds. In the rest of the talk, I'll share kind of three key learnings in building, scaling these systems for detecting content violations. Let's first look at data collection. So data is the foundation of all real-world ML systems. In many of the talks this week, we've looked at the importance of data quality and quantity in making these systems work in the real world. How do we collect this labeled data to train models for integrity, though? Unlike applications like search and recommendations, where user feedback in the product can be used as proxy labels to train the next iteration of models, with integrity, we don't have any such user-generated feedback. And ideally, you want to catch and take action on most, if not all of this content before any user has to even look at it. So in my experience, there's these three stages of maturity that most problem domains go through. At the very beginning, you've probably just defined the policy, and you don't even have any model or rule enforcing on this policy in production yet. At this stage, you might want to start with something very, very simple, things like handcrafted rules, regular expressions, keyword matches, and so on, and send candidates that are retrieved using such simple heuristics for human review. For annotation, the goal here is to start this data collection cycle. After some time, you probably have some rules, some models in production. You've collected some amount of label data. At this stage, techniques like active learning can be very impactful for sort of intelligently prioritizing what you want to label next in order to improve model performance as quickly as possible. And then once your problem domain matures, the ongoing data collection efforts are all about solving for the long tail, and we'll get to that in a second. Let's look at active learning next. Active learning is a collection of techniques that help you intelligently select and prioritize what data should be labeled next in order to improve model performance by looking at some characteristic, some properties of the current enforcement setup. There's two categories of techniques that are used within active learning. The first is uncertainty-based, where we prioritize what to label next depending on kind of what the current model is the most uncertain about when it's making predictions. And there's a few different ways to estimate this uncertainty. For example, sampling examples that are very near to the decision boundary is a common way to do this. Computing entropy of model prediction scores is another way to do it, and so on. And the second category of techniques is what I'd call diversity or representation-based, where kind of we want to prioritize what to label next depending on kind of what is the most different or novel in your inference traffic stream compared to the current training data. And the way you would typically employ these active learning approaches is to go through a few cycles of data collection, model training, and evaluation before your models get to a place where they're performant enough and can serve live traffic. So once your problem domain matures, it's all about solving for the long tail. A majority of new violations on an ongoing basis are likely to be in the tail. And ML model development, kind of beyond a certain stage of maturity, right, is primarily about collecting this new data, adding it to your training set, retraining your models, and making sure that you tame the tail. And taming this tail is all about kind of operationalizing best practices to be able to do this at scale, efficiently, and in a repeatable fashion. So let's look at some components of this. First, you want an edge case detection engine. So that lets you collect this long tail data on an ongoing basis. This could be based on rules. For example, you might want to collect user-reported content. You might want to collect content that is generating a lot of angry reactions and kind of polarizing debate online, and so on. The second step is model retraining. You want to invest in infrastructure and even like an ML team culture that prioritizes and incentivizes retraining, refreshing models on an ongoing basis. Once and done approach just does not work for most ML systems, and especially not for integrity. And the third is model evaluation and pre-launch diagnostics, which we will look at next. So unbiased and accurate evaluation of models is a critical part of the ML development lifecycle. And the most important aspect about this evaluation setup is to make sure that we're doing this in a way that proxies the real-world performance of the models, right? Since we're doing this before launch, we want to make sure that whatever signal we get from it actually aligns with model's performance post-deployment. And there's two parts to the setup that are critical. The first is the dataset. What dataset is the model's performance actually evaluated on? It should accurately represent traffic that would be seen by the model after launch. And the second aspect is the metrics. We want to make sure that we're measuring model performance on this evaluation dataset in a way that actually aligns with the downstream product and business metrics. For a setup like integrity, for example, just measuring raw accuracy would not be a very accurate evaluation setup, given that most examples in your evaluation setup are not going to be a violation in the first place. And so we want to track things like recall of the violating class at a given precision threshold. Let's dive a little bit deeper into dataset construction. So to recap, we have this content stream. We have a combination of ML models, rules, and so on. And then what comes out at the other end is a label on each piece of content in that stream, whether it's a violation or not. How should we sample data from the stream in order to construct our evaluation set, right? Should we sample from the entire stream? Well, a large fraction of this is actually auto-decisioned. And using auto-decision labels as ground-truth labels can be noisy, and it can reinforce kind of the current model's blind spots. Should we sample only from the fraction that is sent for human review? This is a very different underlying distribution compared to the entire stream, right? And kind of just evaluating the model's performance on this narrow slice of data might not tell us how well it'll do on the entire stream. So let's look at this setup in a little bit more detail. We typically have some production model, let's call it M1, to detect violations. And we want to evaluate a new candidate model, let's call it M2. If you look at the Venn diagram on the right, orange is a subset of the content stream that has been flagged by M1. And blue is the subset that has been flagged by M2. And we have ground-truth labels for everything within orange. But we do not have ground-truth labels for like this kind of small sliver of the stream that is M2 minus M1, right? Because these never went into human review. And hence, this is part of the content stream that we kind of just don't have any ground-truth labels for. And if we evaluate both of these models, M1 and M2, just on the subset of the stream that already has labels, we'll end up kind of underestimating the impact of the new model, right? Because it just wouldn't be able to tell us kind of what is the recall improvement. And so how do we solve this problem? One evaluation design that worked reasonably well for us was to evaluate both the models on the entire stream, but then collect labels on a continuing basis in like a lazy fashion once model predictions are known. What do I mean by that? So both models, M1 and M2, produce model predictions. And we give both of these models the same amount of budget, call it top N, decision by their model prediction scores to catch as many violations as they can. And then if you look at the subset of violations flagged by both of these models, we end up with the Venn diagram that we saw on the right. And it has 3 regions: flagged only by M1, flagged only by M2, and then flagged both by M1 and by M2. And we can sample from each of these buckets and estimate the bucket level precision through human review. And then from there, we can estimate metrics like relative recall and additive recall for each model, ones that are already in production, and then ones that are also new model candidates yet to be launched. And based on that, we can make a launch decision on kind of whether M2 should be launched and replace M1, whether M2 should be launched and M2 should also be still there in production because both of them have some non-overlapping contribution to overall recall, or should M2 not be launched at all. Lastly, let's talk about adaptiveness. Integrity systems should be built for adaptiveness and not perfection. We expect platform integrity systems to do well in the real world. And the real world evolves, changes all the time, sometimes abruptly, sometimes adversarially. Consider a model in this example to detect political content online. Over like the last 2 years, let's look at some common topics of political conversations in the US. Everything from COVID and the US elections in 2020 to the January 6 riots, COVID variants, vaccines in 2021, and then this year so far, the war in Ukraine, inflation, economy, and the upcoming midterms. It's nearly impossible to prevent the impact of such changes on the models or even human review performance. And adaptiveness is really the only game in town, not just for models, but also for policies, for human reviewers, for measurement, and so on. And I'll highlight a few learnings on this next. The first learning on adaptiveness is comprehensive end-to-end measurement. How do we know how well is a system working end-to-end? Measurement is the first step to building adaptive systems. And there's two kinds of things we want to measure. Ones that require ground truth labels, for which we need a dedicated set of measurement reviewers. This can tell us things like, what is the enforcement performance? What are the kinds of false negatives and false positives from our enforcement setup? What is the background prevalence, i.e. the pre-enforcement prevalence in the raw content stream before we do any enforcement, and so on. And then there's some kinds of measurements that we can do that are purely just based on the statistical properties of the input content stream. Things like drift, outliers, novel concepts that are emerging, new topics of discourse, and so on. And both of these are important. Three characteristics of this end-to-end measurement setup that make it super actionable are that it should be fine-grained, real-time, and attributable. What do I mean by each of these? Fine-grained in the sense of any quantity that we measure should be able to be measured not just for the entire stream, but also for important slices of our data set. Things like, what is the recall in a given country? What is the recall for the subset of the content stream that is in a particular language, and so on. It should be real time in that we should continuously sample from our stream and have an SLA for measurement reviewers that's on the order of at most a few hours. This is critical to have a real-time pulse on enforcement quality. And it should be attributable. Every enforcement action that was done on a piece of content, we should be able to understand what was the source of that, which models flagged it, who reviewed it, which version of the policy was used to review it, and so on. And this helps us debug and understand the source of any given error. Second, learning on building enforcement systems is to leverage content similarity. When you come across any given instance of a hateful meme, a piece of misinformation, a scam, and so on, right, that was missed by our enforcement, chances are there isn't just one copy of it, but thousands of it online on the platform, maybe with minor variations. How do you deal with this problem at scale? It's not really feasible to have the entire stream be reviewed by human reviewers. And waiting for enough instances of this new category of violation to be labeled by human review and then training a classifier for it is not really feasible either. Like pretty soon, the ML team is just managing these one-off classifiers that number in the thousands. A different formulation of the solution is perhaps helpful here. Can we use the few instances of this new class of violation that we have detected as queries to search for similar content? There's three infrastructure components here that can make this possible. First is embeddings for representing content that are good at near duplicate detection. So broadly, these are embeddings that would map content that are syntactically and semantically similar, very nearby in some latent embedding space. Second, indexing content for kind of fast nearest neighbor retrieval. And the third is some verification or filtering module to filter out false positive matches from the approximate nearest neighbor search. So think of kind of the nearest neighbor search as the L1 ranker and the verification module as the L2 ranker, if you're familiar with search ranking terminology. With this setup, here's how we might solve our problem. For enforcing on all the content that was indexed in the past, we can index all uploaded content within a given time frame and use the few instances of this violation that we do have as seed queries to retrieve things that might be similar and were uploaded, say, in like the last 30 days. And verify, filter out the false positive matches, and then enforce on all this content in bulk. How we might enforce on new instances of the same kind of violation that are uploaded in the future. We can index all known violations till date. And then any new content that is uploaded gets matched against this database. And if it is found to be a near duplicate of something that is already known to be a violation, we can enforce on this automatically without needing human review on an ongoing basis, right? And this index is updated in near real time so as to ensure that our system is adaptive. The last thing I'll highlight on adaptiveness is the following. Even though it might at first seem like only a data or an engineering issue, it's ultimately about collaboration and people. It's about all the various teams that must come together and collaborate to build and improve these systems on an ongoing basis, right? We talked about sort of define, detect, and decision as being the 3 pillars of these integrity systems. In reality, these are not isolated and static components, right? These are changing all the time. For example, new policy versions are being updated. We're tweaking model thresholds. We're deprecating and launching new models. We're retraining reviewers. And in order to understand sort of how well each component is doing and where is there room to grow, these systems need to talk to each other, right? And often these are owned by different teams, which means these teams need to talk to each other and collaborate and have like a very high throughput of communication and trust as well. So in conclusion, I would summarize the kind of key takeaways of the talk as follows. The goal of integrity systems is to maximize recall and minimize false positive errors while ensuring that operational expenses, latency are within bounds. In order to get to high recall, it's important not just to do well on the head of the distribution, i.e. the commonly kind of known and prevalent violations, but also on the long tail. And thirdly, we should strive to build adaptiveness and not strive to build these systems for perfection, because the real world changes, and so does the ideal nature and the ideal state of these integrity systems. With that, I will conclude my talk. Thank you all once again for being here, and thanks everyone who's joining virtually as well.
Okay, we have some time for questions.
Sure.
Thank you for your talk. How much of your application, your processing, applies to multimodal inputs, and how much of it is only text-based?
Yeah, so it's very generically applied across modalities. There's parts of this that make more sense for text versus images and so on. For instance, near duplicate detection, for example, is like easier to do with images, a little bit harder to do with text, and like really hard to do with videos. But yeah, I would say
but you treat each of those modes as separate evaluation metrics, or do you combine them into a single decision in your policy?
Yeah, so it depends exactly on the nature of the content that you're dealing with. If these are unimodal streams, then you want to track these separately. But yeah, I mean, most content online tends to be multimodal, and ultimately, kind of, you want to track these things at the level of the entity, right? Like the post, the piece of content, the ad, the message, and so on.
What about the issues of defining the policy and the localization of the moderators?
Yeah.
Doesn't that affect the multimodal inputs? Somebody in the Philippines who's reviewing an English post could come up to a different conclusion than an American native speaker, or an Australian native speaker, or a British native speaker.
Yeah. So I'm not sure I exactly heard the question correctly, but are you asking about localization of policies and of reviewers? Yeah, I mean, it's a hard problem, and I'm not sure if there's like a very clear answer there. You do want to, and again, like depends a little bit on kind of what scale you're dealing with and what kinds of policies. For example, for certain policies like nudity detection, like localization wouldn't have a lot of impact. It's ultimately kind of, you're just trying to detect something that's purely based on content. But then for things like hate speech, misinformation, there's a lot of cultural and language nuance. And yeah, I mean, there's two axes along which you want to do this localization. One is kind of more on the rules and model side, and kind of here, typically things like ensemble models would work well. And then there's localization on the kind of policy and reviewer training as well. Yeah, I mean, one of the things that that I know a few teams kind of have tried out is almost sort of having this optimal reviewer routing, right? So for a given piece of content, you would have a model sitting in between the queue and your group of reviewers that would do the job of like optimally routing a given piece of content to the reviewer, right? And this routing model would encode preferences about reviewers in terms of their familiarity with the language, policies, and so on. But yeah, it's a hard problem.
Awesome. Any other questions from the room? Okay, we have one question online that was asked a little bit earlier. Looks like it's a comment and a question. Active learning with uncertainty sampling is straightforward. How is diversity sampling done, though? How do we identify novel data automatically?
Yeah, so a couple of heuristics that kind of that are commonly used. Ultimately, you want to learn a model for the training data distribution, and then make some prediction about sort of what is like how much within distribution versus out of distribution is a given piece of content in the inference traffic, right? So broadly, kind of, and you can do this globally. You can kind of first cluster your training data set and then do this within each cluster. So there's like a few different ways in which you can potentially kind of set up the system, but the general flavor of kind of the solution would be to learn a model for the underlying distribution of the training data and then use that model's predictions to kind of quantify how much of an outlier is a given point in the inference tree.
Okay, awesome. Thank you everyone for attending. Thank you to our virtual attendees, and thank you to our speaker.
Thank you.